Subscribe now.
This video series on digital signal processing. Specifically, we are going to deal with discrete Fourier transforms, which is DFT. Now, DFT is a powerful tool in the field of digital signal processing, and it allows us to analyze frequency contents of discrete time signals. Right. So, this word of technology, signals are often represented as sequences of numbers that represent the signal's amplitude at discrete point in time. Right. So these signals can represent a wide range of phenomena. That is from audio. It can represent a wide range of phenomenon from audio and video signals, to sensor data and many more, right? Sensor data and many more. The DFT provides a way to analyze these type of signals in the frequency domain, which is a representation of the signal's amplitude as a function of frequency. This is incredibly useful because it allows us to understand the underlying frequency component of that particular signal, which can also help us in the tasks such as maybe filtering, if you want to perform filtering activities. This frequency components will help us in tasks like filtering and also noise reduction. And also something like modulation. So, the DFT can also be defined mathematically as S of k equal to sigma, which is summation of n equal to 0 to n minus 1, and then x of n multiplying by exponent negative j, and then we have 2 pi over n, and then multiply by kn, where this x of k represents the frequency domain representation of the signal. The frequency domain representation of the signal. Also, x of n also represent the time domain. The time domain representation of the signal. N, which is also in the mathematical expression, also represents the total number of samples in the signal. K is the frequency index, which ranges from 0 to n minus 1. That is, let's say, frequency index. And it ranges from k equal to 0 to n minus 1. And we will talk more about it in my next tutorial. Proceeding with this mathematical expression, the exponent negative j 2 pi over n and then kn is also the complex exponential kernel. Complex exponential kernel. So by calculating DFT of a signal, we can actually obtain a representation of that particular signal in the frequency domain, and this will tell us how much of each frequency is present in that particular signal. But when it is in the analog domain, it will be very difficult to estimate the number of frequency present in that particular signal. This information can then be used to perform some various signal processing tasks, as I mentioned earlier. And some of these tasks can also be identifying specific frequency and also removing noise and many more, as I was talking about over here. So in my next tutorial, we will go through the process of how we can calculate the DFT of a signal and also discuss its properties and explore some practical applications. So if you have not subscribed to this channel, please do well and subscribe to this channel and also share to others as well. Thank you for watching and see you in my next video.